Okay, and there's a neat connection between the inverse of a linear transformation and the inverse of its standard matrix. But for now, we're just going to assume that the two notions are completely unrelated and we'll explore them independently, but then we'll very quickly see what the connection is. So the example that we're going to look at is a rotation matrix, right? We've seen this one before, but I'll just remind you. So we've got a transformation T going from R2 to R2, and what it does is it rotates vectors about the origin in a counterclockwise direction by pi over 2. And the standard matrix of that transformation, well, is right in front of you. It's this matrix A. And I just want to remind you where this comes from because we're actually going to need to use this in part C. So what this is, remember when we derived the standard matrix of a general rotation transformation about the origin in the counterclockwise direction by theta. That's quite a lengthy sentence to describe it, but that's what it is. You're taking vectors, rotating them counterclockwise about the origin by some angle theta. And in general, the standard matrix of that transformation is going to be given by what you see me writing down right now. So cos theta, sine theta for the first column, negative sine theta, cos theta for the second column. So this is where this matrix A comes from just by plugging in theta is equal to pi over 2. So it's nothing mysterious. That's where that's coming from. So, okay, what are we asked to do here? First, in part A, we're just asked to find the inverse of A. So that has nothing to do with transformations necessarily. You don't need to make it about transformations. That's completely a matrix issue. And there's a process for finding the inverse of a matrix. You can use the inversion algorithm, but because this is a 2 by 2 matrix, we can just use the inverse formula. Remember, let me just remind you, if you have a 2 by 2 matrix, its inverse is given by 1 over AD minus BC, and then you do some shuffling to each of the entries. The entries move around a bit and some negative signs are introduced, but this is the formula that you use for the inverse of a 2 by 2 matrix. And of course, this depends on this quantity being non-zero. If AD minus BC happens to be 0, well, then this won't work, right? But if that's the case, then the matrix doesn't have an inverse. But in the case of part A, if you work that out with this matrix A, this denominator would be 0 times 0 minus negative 1 times positive 1. That's going to be 0 minus negative 1. So this expression would just work out to being positive 1. So the matrix does have an inverse, and you can use this formula to get it. So let me just do it this way. I'll say A inverse. Here's what you're going to get if you apply this formula. If I swap the two zeros, well, then there's no change, right? If I take the two zeros and they trade places, the end result is the same for those two. But then I'm going to introduce negative signs on the negative 1 and the positive 1, like so, and that's what I'm going to get, right? Because I didn't bother with this because this will just equal positive 1 in the case of this matrix. So this is what you end up getting for A inverse. But just to emphasize, this had nothing to do with transformations or inverse transformations, right? This was completely a matrix issue. Okay, now part B is when we're going to actually work with T. So what does part B ask us to do? It says describe the behavior of T inverse in ordinary language. So what does that mean? Well, this is ordinary language right here, right? We're talking about mathematical terminology, but it's still ordinary language. You're describing what the function does in words. So what would the inverse of T have to do? You're trying to think of a function that would undo the work that T does, right? So T rotates vectors counterclockwise about the origin by pi over 2. How would you undo that and go back to the vector you started with? Well, there's a couple different ways to think about it. Let me draw a little picture here. Let's say we have a vector, and I'll draw it in blue here. I'm not sure why I chose blue, but it doesn't matter. So if I rotate this vector by 90 degrees, it's going to give me this, right? This would be a 90-degree angle. Call that vector x, and call this vector t of x. So how would I undo that change? Well, there's a couple of different points of view. One point of view would be to just rotate it the rest of the way around the circle so that it's back, so that it ends up back where it started, right? So I could just rotate it more, right? Rotate it by 3 pi over 2, because pi over 2 when you add it to 3 pi over 2 gives you 2 pi. And remember, 2 pi would be one complete circle to end up back where you started with. So that's one point of view, would be to just rotate it 3 pi over 2 in the clockwise direction. So that's one approach. Another approach would be just to rotate it in the other direction by the same amount. So rather than rotating it counterclockwise by 3 pi over 2, we could rotate it pi over 2 in the clockwise direction. It's a different action in some sense, but the end result is the same. And for functions, all you care about is input and output. So it's just another way of describing the same task. So let's use the second one because it's simpler. So let's say this T inverse rotates. Let's be really pedantic here and be really careful with our words and write this out very precisely. So T inverse rotates vectors clockwise. I'm going to really underline that twice because so far every rotation we've talked about has been counterclockwise. So T inverse rotates vectors clockwise about the origin by pi over 2. Okay, but what else can you say? Right, we don't need to give a formula for it. That's not what was asked for. We were asked to describe it in terms of words. Now, giving a formula for how that's going to be accomplished, that's essentially equivalent to finding the standard matrix, and that's what we're going to do in part C. We're going to find the standard matrix of this inverse transformation. Okay, well, let's do it. There's a couple of different ways you could do this, and that's the territory for linear algebra. You've probably noticed that already. A lot of the problems you work on, there's many different approaches, and sometimes there's some approaches that are simpler and probably objectively better for that reason. But lots of times, it's a free for all, right? Use whatever method you want. You have lots of options at your disposal. One of the ways we could do this, that it doesn't involve machinery, would be just to say, well, how do you find the standard matrix of a transformation? Figure out what it does to each of the standard basis vectors. So we could figure out what T inverse does to E1 and E2, and then take those to be the columns of our standard matrix. But what we'd be doing is we'd essentially be repeating the argument that we gave when we derived this matrix, which, remember, this matrix is how you rotate vectors counterclockwise about the origin by theta. So we could just use this as theta. Or pardon me, we could just use this formula and then plug in our appropriate value of theta. Now be careful, we're going clockwise, right? So we can't just plug in theta equals pi over 2 or we'll end up getting this matrix again. So how do you factor in the idea that you're going clockwise? Well, we could just go back to the idea of saying, well, why don't we just rotate it clockwise by 3 pi over 2 and plug in 3 pi over 2 for theta. Remember the first picture I drew down here before I erased it? We could just plug in theta equals 3 pi over 2 right here. But alternatively, if you want to capture the essence of going counterclockwise, just put a negative sign on the pi over 2. Right? So that's the simplest way to do it. Just take this matrix, this general matrix for a general theta rotation, and just plug in theta equals negative pi over 2. So the standard matrix of T inverse is going to be cosine of negative pi over 2 for the first entry, sine of negative pi over 2, then negative sine of negative pi over 2, and then cosine of negative pi over 2. And it just comes down to evaluating trig functions. So draw the graphs, use special triangles, use the trig table, do whatever you got to do to evaluate the trig functions here. But what you're going to end up getting, cos of negative pi over 2, that's going to be 0. Sine of negative pi over 2 ends up being negative 1. Negative sine of negative pi over 2, that's going to be negative 1. And then cosine of negative pi over 2 gives you 0 again. So you end up getting, hey, 0, negative 1, positive 1, and 0. And if I'll just draw a box around my answers for all these parts. This was our answer to part B. This was our inverse of the matrix A. And this was the standard matrix of T inverse. What do you notice about your answers to part A and part C? They're the same. So how did this happen? Again, let's remind ourselves the context. We've got a transformation T that's invertible. It had a standard matrix. If you treat that matrix as just a matrix and take its inverse using the normal matrix tools that we have, it looks like you'll get the same thing that you get if you go back to the transformation, figure out what the inverse transformation is. So now you're talking about a transformation inverse, not a matrix inverse, a transformation inverse. But then what happened? We took the standard matrix of that transformation inverse, and we ended up getting the same thing we got if we just took the matrix inverse of the standard matrix of the original linear transformation. I know there's a lot of jargon there, so it's so you may have to pause that or rewind and listen to it again slowly, but that's what we did. Okay, and it may help to think this way in terms of this diagram. Okay, let me just draw a line here. I find this diagram helpful. So a transformation T corresponds to a standard matrix, right? Okay, and then this assumes you have an invertible transformation. So this is a transformation inverse that brings you to T inverse. Now T inverse, or let's come back to T inverse. Actually, this matrix A, we can also take its inverse. Okay, and then we'll get A inverse. So here's what happened, right? We had our transformation T. We were given the standard matrix up here. We found its matrix inverse. But then in part B, we said, okay, forget about the standard matrix for a moment. Consider the transformation inverse, T inverse. And then in part C, we found the standard matrix of T inverse, and it turns out they were the same. That's what happened here. That's what the observation was. Now, will that always happen? Is that always going to happen, right? Is it possible that if you start with a transformation T, figure out its standard matrix, and take the matrix inverse of that standard matrix, is it possible that you could go now the other way around this diagram, go for the matrix, or find the inverse of your transformation, then find the standard matrix of your inverse, but then not end up with the same matrix? And actually the answer is no, that'll never happen. So this diagram commutes. This is what we say in mathematics. This diagram commutes. That's what that symbol means. It just means no matter which way you go around this diagram, you're going to get to the same place. You're going to have the same outcome. Okay, so that's what this fact is outlining. So it's depending on how there's simple ways to phrase this, and there's complicated ways to phrase this, depending on which jargon you're willing to use. But if you accept the jargon, it's actually not too bad. So if you have an invertible linear transformation T, and you have the standard matrix of that transformation, call it A, then the standard matrix of the inverse transformation is just going to be the inverse of the standard matrix A of the original linear transformation. And that's the essence of what's happening here. So there's a really tight-knit correspondence between matrix inverses, the idea of matrix inverses, and the idea of transformation inverses. And roughly speaking, they are the same notion, just with different terminology and different notation.